All right, my friends, this is where we landed yesterday. I think this was the last slide that we saw, where we saw the energy levels and sublevels being arranged or ordered from the lowest energy down here at the bottom as close to the nucleus, and then upward gets us farther and farther from the nucleus. I've got lots to do with this arrangement and this today. I think, finally, if the last few days, after all this bombardment with different scientists and what they did, and does it make any sense, and how does it all fit together, it's going to start coming together really well today. I'd like to begin with an exercise similar to one of them that's in the book, at least one of them that's in the book. It's where you'll be given some quantum numbers, and the question will be, how many electrons can possibly have these given quantum numbers? And you may not be given all four. Like in this case, we're given 3 quantum numbers. How many electrons could be described with those? Take a look at the first one. If n is 0, L is 0, and m sub L is 0, even if we don't know the m sub s, how many electrons could have those 3 quantum numbers? No? Yes. 0. This was a tricky one. I shouldn't have started with this maybe, but I did. Why 0?
L can't be 0.
L can be 0. Yeah, right. We can't have an n value of 0. Yep. N can't be 0. So if n is any other integer, then we could have some electrons, but not for n equals 0. Okay, so let's try another one. This time we're given all 4 of our quantum numbers. 2, 1, -1, and -1/2. How many electrons in an atom could have those quantum numbers? Is that you that said that, Claire? 1 is right. Yeah? Can you justify that? Why?
All 4 are already there.
Yes, all 4, right, because you have all 4 quantum numbers. I had mentioned this yesterday. This has a name. It's called the Pauli exclusion principle. If you're given 4 quantum numbers, only 1 electron can be represented by those 4 quantum numbers. No 2 electrons can have the same set of 4 quantum numbers. They can't. They'll all be unique. If I take you back, now look at what these quantum numbers are. N value is 2, and the L is 1. Do you remember what letter designation goes with L equals 1? P, right. If L equals 0, that's called S. If L equals 1, it's P. If L equals 2, it's D. And L equals 3 is F. So we're talking about an electron somewhere in 2p. Yes? Now, remember, if L equals 1, that's a p, and m sub L goes from -L up to positive L. So if L is 1, there's 3 possible values for m sub L. -1, 0, and positive 1. That's why, for all the p's in this diagram, there's 2p, there's 3p, there's 4p, there's 5p. All the p's have 3 lines next to them. Those lines are orbital orientations. That corresponds with the number of m sub L values. So in, let's see, what do we decide that was? This is 2p. So we're talking about, on this line right here, 2p, what was the third quantum number? Was it -1? Okay, so the m sub L values go from -L up to positive L. And so we're talking about an electron that's on that line right there. And the quantum number even tells us what direction the electron is spinning. If I remember, it was a -1/2 spin. So that means it's a down arrow on that one line. That's 1 electron that has those 4 quantum numbers. No other set of quantum numbers is going to get us to that spot. Only that 4 quantum numbers. Yes? Mm-hmm. So those 4 quantum numbers, anytime you're given all 4 quantum numbers, that corresponds with 1, as long as they're valid quantum numbers. 1 electron. Okay. Oh, yeah. This one, you're given 2 of the quantum numbers. You're given the n value and the m sub s value. How many electrons could be described by those quantum numbers? No? You're close. You're adding wrong. Unless I miscounted your fingers. Hold them up again. Yeah, no. No. No.
It's not 9, is it?
9.
Oh.
9 it is. When your feet get back on the ground, Matthew, how do you come up with 9?
So if n is 3, then L can be 0, 1, or 2.
Oh, yes. Oh, I just did this wrong. The n value is 3. So we're talking, I'm just going to get rid of this. We're talking about this, this, and this. Those are the 3 sublevels in the third energy level. Yeah? Keep going.
So if the sublevels can be 0, 1, or 2, that means we can have 1 orbital for the 0, 3 orbitals for the 1, or 5 for the 2.
And the m sub s is positive 1/2. What does that mean?
1 electron per orbital.
Yeah, only 1 electron that is in the up direction, or positive 1/2 spin. So we're talking about in 3s, there's 1 line, you can have 1 up arrow. And then the next electron in there is the down arrow that can't have a positive 1/2 spin, right? And so in 3p, you have the 3. In 3d, you have the 5. Okay, now I want to ask you, get into your head, where did you get 10 from, Nathan? Is that what you're trying to do, count up these?
Oh.
And Laura, where did you get 6?
I don't even know.
Okay,
I was, yeah.
you weren't thinking like that?
No.
Okay. And somebody else gave something. Oh, Kevin, you came up with a number 2. Where'd you get yours?
I forgot to count the D.
The 3 Ds? Okay, okay. Yeah, yeah. Are we okay with that one? These are good exercises. It makes us think about what the quantum numbers tell us. Here's another set. This is only 2 quantum numbers given. How many electrons can have the quantum numbers n equals 2 and L equals 0? Hold the number up. Uh-huh. Yeah, Billy, you're right. Nathan, you can count this time? 2. Because if we're in the second energy level and L equals 0, that means we're in 2s. And we don't have any of the other quantum numbers, so that means that all of the number of the electrons that can go on 2s only would qualify. So there's 2 electrons. Yep. Ask if you have any questions about any of these. Finally, I think this is the last one. Given these 3 quantum numbers, 4, 2, and 0 for n, L, and m sub L, how many electrons can have those 3 quantum numbers? No? Yeah. N equals 4, we're in the 4th energy level. L equals 2, so 4 what? SP, D, or F? D, 4D. We're in 4D with these first 2 quantum numbers. And then the m sub L is 0. That m sub L is what gets people. So we're in 4D. We're in this thing right here, somewhere. And it says that the m sub L value is 0. The m sub L corresponds with which line the electrons are on. If L equals 2, that means that m sub L goes from -2 to +2. And there's why we have 5 lines in all the Ds, because the lines correspond with the m sub L values. Now we're talking about m sub L equals 0, and it's that line right there. There's room for 2 electrons. Yeah? Okay, so that's our, that's just the little quantum number practice. To be honest with you, I don't like this slide. There's a lot of chemistry textbooks that will give this arrangement of electrons. Oops. You do need to memorize the order of these. 1s, 2s, 2p, 3s, 3p, and then 4s before 3d, like that. You need to know those. What I teach in Chem 1, I'll share the same thing with you. If you try to brute force memorize this, how come I lost one in here?
It's at the bottom right corner. You moved it.
I would have been looking for a long time. Thank you. Weird. Okay, so anyway, yeah, I don't want you to brute force memorize these. It's way easier just to use a periodic table. The rows on the periodic table correspond with energy level, electron energy levels. In the first row, we're talking about the first energy level, very close to the nucleus, 1s. In the second, and remember, how many electrons can 1s hold? 2. So there's 2 elements in the first row, first energy level. In the second energy level, there's 2s and 2p. The 2s can hold 2 electrons, that's Li and Be. The 2p can hold 6 electrons, that's boron through neon. You know what is so cool is this periodic table was developed and looked like this without as many elements on it back in the, well, it was the early 1900s, in the first decade of the 1900s. A guy named Henry Moseley came up with this. It was after Mendeleev came up with a periodic table in the 1860s, but Moseley realized that it should be arranged with the atomic number increasing. Mendeleev has atomic mass increasing. And Moseley modified a little bit about it. Schrodinger came up with his wave mechanical model in the 1920s, the mid-1920s, 1925. It turned out that the solution to the Schrodinger equation placed elements exactly as Moseley had placed them back 15 years before that, or 20 years before that. And there was really no collaboration of Schrodinger with where things were on the periodic table. It just happened to fall like that. So when I say that the 1s has room for 2 elements, or 2 electrons, there were already 2 elements in the first row of the periodic table by Moseley. And the second row has room for 8 elements. There's 2 in 2s and 6 in 2p. They were already there. It's so good. And the Schrodinger model fits perfectly with the periodic table. That to me is pretty cool. So yeah, the periodic table in the other room has its rows numbered. So next to hydrogen is 1, next to lithium is 2, next to sodium is 3. 1 through 7, Francium would have 7 as the 7th row. And all you have to do is recognize that the S's and P's, S's are on the left 2 columns, the P's are the right 6 columns, and then in the middle here, these lower families, those are the D's. The S's and P's are the same as the row number. So in the first row is 1s, second row is 2s and 2p, third row is 3s and 3p. When you get to the fourth row, then you're going to get some D's in there. And remember, D's are where we get the overlap. So you got 4s and 4p, and that's kind of got 3D in the middle of it. In the fourth row is 4s on the left, 4p on the right, but in the middle is 3D. So if you can just remember, S's and P's are always the same as the row number, same energy level as the row number. The D's are 1 less than the row number that they're in. And that's memorizing that whole order of things. The F's get messy. I mean, you'd get CS and BA in the 6th row, so these would be 6S, and then you have to remember to come down here to 4F. After 6S is 4F. That's on there. But I would say, if you can remember up to xenon and not even worry about the F's, it's fine. It's good. Oh, hey, Emily. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. That gets us to the end of the 4th row. 5th row, 5s, 4d, 5p. 6th row, 6s, 4f, and then up to 5d and 6p. So S's and P's, even if there's stuff in the middle, are always the same energy level as the row numbers. Anybody have any questions about that? Now, there is a cutesy way of coming up with the order of energy sublevels. It's called the Aufbau principle. I just think it looks dumb and messy. And probably my problem is, when I write stuff, I can't write organized enough so that my arrow goes through. If you write it correctly, the arrow that you start, and you write it on a 45-degree angle downward, it should go through the energy sublevels in the order that they happen. If you just start in the top right, tail end of the arrow, 1s, 2s, 2p, 2p, 3s, and then 3p, 4s, and then 3d, 4p, 5s, like that. I don't know. You can look at it. This would be pretty significant and important. This kind of thing, with this formula right here,